There is some question in the chat. I'm not sure if you noticed. Maybe we can take it later on if it requires a bit more.
Sure. Yeah, I just saw it now. Yes. So such a tildes do always exist. So I guess by low degree here, we allow the thing to have even linear degree. So it's not like constant degree. So for any Boolean function, there is always, in fact, like a multivariate multilinear polynomial where there's no squares in it. But here we allow there to be some squares for technical reasons. The multilinear case doesn't always capture what's going on in some of these other things. So it's like actually poly in degree. So those, yeah, in those cases, a tildes do always exist. The extra degrees in the variables only make sense once you start querying non-Boolean points. Like on Boolean points, like raising a variable to a power doesn't. So yeah, on 0, 1, right, the raising variable to power doesn't change anything.
Right. And well, if you have any further follow-up questions, you can write them in the chat as well. But anyway, I guess we should slowly start the second part. So yes.
Yeah. Sure. Right. The relativization barrier and non-relativization, how to get around it in some cases. So next, as promised, we'll talk about the so-called Rasburov-Rudish barrier, aka natural proofs. So it's usually called the natural proofs barrier, but it's not really proof theoretic, as you'll see. But it is a real barrier. So it's a barrier to lower bounds against classes like this p-poly. And I've kind of only alluded to non-uniform circuits and so on, but let me make sure that the definition here is clear. So this is a class of functions, which are usually the decision problems, and it has the property that for all constants c, there exists a constant c, so that for all n, the nth slice of the function, so the function restricted to n-bit inputs, that slice has a circuit, let's say over n, or a knot of fan n2 of size into the c plus c. And this into the c plus c is just a proxy for polynomial size. And so it's saying that we get to design like an infinite sequence of circuits, right? One for each input length, okay? And we just require that the nth circuit has polynomial size, okay? This is a non-uniform model in the sense that actually writing down the entire description would be infinite. But the point is that the amount of work, the amount of description that's used for n-bit input is only polynomial nn, okay? And so, I mean, p-poly is like the major class to think about when thinking about circuit complexity, like circuit complexity of like decision problems. I do want to add that depth restrictions on p-poly, like making them have logarithmic depth, or even making them have constant depth with gates that can take in arbitrarily many inputs, this will yield weaker classes, which have various names: AC0 parity, TC0, NC1. I don't think, I mean, I'll bring up these names if they're important for the particular example I'm looking at, but other than that, I'm just wanting to name drop and leave it like that for now. The big conjecture about p-poly is that NP is not in p-poly. Now, we know that P can be simulated in p-poly. So this would imply P different from NP. And that makes this problem only harder than resolving P versus NP. But people turn to this problem, let's say, in the early 80s, when looking at relativization, they were okay, well, maybe you can get around the relativization barrier, like trying to reason about Turing machines by reasoning about circuits instead, like, simple things made out of and, or, and not. But it remains open, I should say, whether non-deterministic exponential time is in p-poly. I mean, this seems pretty absurd, like it's exponential time and it's got non-deterministic, so it can guess exponentially long things. And we're asking whether it has polynomial size circuits. So like if I get to restrict this for each input of length n, I magically get some polynomial amount of work that will solve any nx problem. Almost certainly no. We have some ways of attacking this question, as opposed to like other questions, like I would say P versus NP, we still don't really have a good attack. But nevertheless, it remains open. And this is just to illustrate how difficult circuit lower bounds are. But there are many other ways to illustrate this. This is just one of the many pictures in the gallery of reasons why circuit lower bounds are hard. So Rasbarov and Rudich were trying to understand, the difficulty of circuit lower bounds. And so they were saying, what are some common properties of lower bound proofs? So they wanted to say, abstract out what's going on of a lot of these lower bounds that happened in the 80s that worked against like weak classes, like constant depth circuits with like ands and ors of unbounded fan-in, unbounded number of inputs. They could not extend, as far as people could tell, to even like log depth circuits, like just like NC1 or polynomial size circuits. So they want to know, okay, what are some common properties these things have? So like the first step is, okay, you identify some property P of Boolean functions, right? It's true or false of each Boolean function. And the idea is this property P is supposed to distinguish hard functions from easy functions in one way or another, okay? So just to give like a small number of examples, there are many more in the Rasbarov-Rudich's paper, like F is non-degenerate, like it depends on all of its variables. This is like a very weak version of hardness, but like it doesn't depend on like, I don't know, 3 inputs. It actually crucially depends on all of its variables in some important way. Okay, and there's a way to formalize what this means. We'll see. Another property is that, slightly more interesting, is it does not become trivial. It does not become a constant function after, say, partially assigning most of its variables. So the function to keep in mind here is the parity function, like takes the sum modulo 2, right? It doesn't matter if I restrict n minus 1 out of n inputs, it's still not a constant function, right? Flipping, like setting the last bit will flip the bit, right? One way or the other, okay? So it does not become trivial after some partial assignment to most of its variables, but that's actually true for like circuits of unbounded fan-in, so ors and ands of constant depth, okay? So just to draw a picture, like unbounded fan-in and but like constant depth, so constant number of layers, but these are still polynomial sized circuits. I don't get like exponential fan-in. But yeah, so this kind of property is used to prove that the parity function cannot be done in constant depth with ors and ands. Okay, this kind of property. Okay, another property I just want to throw out there, but I mean, just you can if it's tantalizing, you can look it up. But just wanted to say one more thing about these things. So F is so-called versatile. This is a term I think first given by Smolensky. And it basically says that many functions, other functions G, can be expressed as like a low degree polynomial. In this case, low degree means degree at most n over 2, plus another low degree polynomial times F. Okay, it's just some way of expressing many possible functions. So F is like you can think of it as some kind of reduction. I can reduce G to the computation of F. Because P1 and P2 are like degree lower than n, F has got to be pretty interesting. It's got to be almost like a basis function for whatever space of polynomials you're looking at. Okay, so this is used in Rasbarov work on constant depth lower bound Smolensky. So like, for example, you can show the majority function is not computable. Even if I allow you, so like a parity gate, so allow you to compute the parity along with ors and ands and constant depth, you can't compute the majority. And there's many other lower bounds like this. So you wanted to find some property, right? When this is true, then it's hard in some sense, but it's hard for like a weak class. Okay, so being non-degenerate is like a very weak property. It's hard. I mean, it means the circuit has to have like at least n-1, let's say, gates in it or something if it's fan in 2. So, but it doesn't say much more beyond that. Okay, so you identify some property. Okay, the next you show that this property is not difficult to check. Okay, so there is some algorithm that will decide the property, true or false. Okay, and it takes polynomial and to the n time on truth tables of length to the n. So it just takes in a truth table of a Boolean function and gives you a true false answer. All right, and it does so in polynomial in the input, which is of length to the n. Okay. All right. The other properties are kind of what we mentioned before when we were talking about these probabilistic methods. So the next property is that for all functions, so if we think of a decision problem as like a collection of these like finite slices, so where like the n-bit strings are handled by f sub n, if this property is true for infinitely many n, then f is hard. Okay, so this is something that you kind of have to have for some lower bounds. So we're basically showing that f is not in some class C. Okay, so in other words, this property actually relates to the difficulty of some problem. Okay, this is just kind of slightly formalizing what it means to distinguish hard from easy. So when this thing says true for infinitely many n on these n slices, then f really does correspond to some hard function. Like let's say it's not in AC0. It's not in constant depth if it has this property holding for infinitely many n. Okay, and the next property is that if I give you a random function, okay, this is true for all n, the probability the property outputs true is at least 1n to the n. Okay, and you could imagine this being a larger thing, but let's just say it's non-negligible in the input length because the input length is 2 to the n, right? So it's just like 1 over input length, right? So the probability a random function is hard is non-negligible. And this is something we would expect from any property that's correlated with high circuit complexity, as most functions have, say, exponential circuit complexity. For essentially any interesting model you have a circuit complexity where like a gate is not doing too much work or a step is not doing too much work, because the functions take 2 to the n bits to describe, most functions are gonna need exponentially many gates or operations to compute them. All right, so these are like the common kinds of properties. There's some algorithm deciding the property. If the property is true for infinitely many n, the function is actually difficult, and a random function is going to be considered hard. The property would be true of it. All right. So this leads us to this definition of a natural property. Okay, so we say algorithm A is a natural property if it is both constructive and large. And constructive just means that the algorithm runs in polynomial time in its input. Okay, so for all n, for all truth tables of length to the n, it halts in poly time. Okay, and it outputs a 0, 1 answer. Okay, so it's like a true false. It's declaring true or false. And then it's large if it outputs 1 with non-negligible probability. Okay, so for all n, if I pick a completely random function, it's going to output 1 with probably at least 1 n to the n. Okay, no, this is the space is to the n possible Boolean function. So this is like 1 over the input size. Okay, so it's not that negligible. It's non-negligible. Okay, so that's what we mean by natural property. All right, it's poly time. It outputs 1 for at least a 1 in n fraction. Now, to use such a thing for lower bounds, it needs to be useful. Okay, and so we say it a property is useful against a class C if for every function in that class, which we can think of as a infinite collection of these finite slices, things that take n bits and output a bit, okay, there must be infinitely many n, so that this property outputs 1 for some function, okay, for some n-bit Boolean function. And yet on this class, it outputs 0, okay? Now, this is like the weakest notion of usefulness you could think of. So like we're saying the property, okay, it's declaring kind of all these, or infinitely many n, is declaring these finite slices to be easy, okay, of every function in this class, but like some other function is declared to be hard. So this is just to rule out it being trivial and just always outputting 0, okay? All right. So this is like this is absolutely necessary. It's useful if it distinguishes every, say, function in here, roughly speaking, from some function G. Okay, you got to have that to have some kind of lower bound. You have to have some kind of property that is doing this. Now, if you're proving a specific function is hard, right? If a specific G, it cannot be some G. It has to be the same G is being declared like over all functions. So if I'm saying that like a particular G is not in the class C using this thing, then it needs to be that like that. So there's no quantifier here. That like this G is like out here, and it's always for infinitely many n, this thing is being declared hard, but the other thing is being declared easy. I mean, and that's just like if we forget about like the constructive and large thing, this is something that just has to be true. Like if the thing is not in the class, there's going to be something that distinguishes it from everything in the class. Okay, so that's why I'm just emphasizing that usefulness is actually necessary in a certain formal sense for proving a lower bound. Okay, like so like a natural proof that G is not in C, a natural property would have this algorithm. It's constructive. It's also large, and it is outputting 0 on all the easy things in the class C, and it's outputting 1 on the function on finite slices of the function G. Okay. Does it make sense?
Seems so. There are no questions.
Okay,
So
there's
far.
a thumbs up. Okay,
Yeah.
okay. All right, good. All right. So just to give an example, so I'll try to just give simple examples. I mean, there are certainly complicated ones. So that like just checking whether a function is non-degenerate is natural, and this is used to prove some pretty weak lower bounds. So what do we need to do to check non-degeneracy? We check that for every variable, say index 1 through n, there is some assignment to the inputs, so that flipping the ith bit, from 1 to 0 changes the value of the function. Okay, so in this sense, like every variable affects at least one assignment. Okay, so this is what we mean by non-degenerate. Okay, now, okay, it's constructive because given the truth table, you can just check this by going through every n and trying to find an assignment. Right, there's 2 to the n assignments. We go through every n, like we imagine, say, random access into the truth table. And so in checking n times 2 to the n conditions, right, we can check this, right? Once we get one assignment, we just flip the bit and check that, all right? So it's clearly constructive. It can be checked very efficiently given the truth table. It's also large, and this is not too hard to see. If I take 2 distinct strings, the probability a random function is the same value on those strings is a half. Okay, because fix one of them, the other one it agrees with probability a half, right? So the probability that a function is degenerate, so it's not non-degenerate. So this is this is the same as like we want the probability that there exists an I, so that for all assignments, the function stays the same if I flip the ith bit. Right, so this is just negating the condition up here. So there exists an assignment. So for all assignments, the function stays the same when I flip the ith bit. There's an equality. Right, so just by the union bound, I can sum over all the choices of I and compute the probability that for all A, they actually agree. And so using this fact, we just get that this is at most n. It's coming from here over to the n. All right. Okay. Okay. So checking non-degeneracy. So the point is that's like degeneracy. So non-degeneracy is actually going to happen with super high probability. Okay. All right. So slightly more complicated example. Consider the restriction method for proving lower bounds. Okay, and this is roughly saying that we want to know whether if I restrict some n minus 2 log n variables, all but some small number of variables, do I make my function the constant function? Okay, so the negation of that, saying that it's hard, is saying actually for all the possible ways that you might assign 0, 1 values to all but 2 log n variables, the function you get after this assignment, that's what I mean by this restriction, is not constant. There's some other, it's still going to be not constant. So like the parity function, for example, this property is true. Like you got to assign all the bits of parity for it to finally become constant. So even if you leave something unset, you can flip the bit of parity. But it's not true of, say, small constant depth circuits using ORs and ANDs. Okay, so things like this are used to prove lots of lower bounds against constant depth circuits, and they're always natural, as we'll see. So for one, it's constructive. So to check this property is constructive. So what do we have to do? Given such a function, we try all possible ways to assign up to n minus 2 log n variables, right? And then we output 0 if and only if f is constant on one of those ways. Okay, so just a really crude upper bound on this, just to show you that it's following on time. There's at most 3 to the n partial assignments to bit strings, right? Like if I just work over the alphabet 0, 1, don't care, right? Like don't assign, right? There's 3 to the n possible partial assignments. Okay, so there's no more than 3 to the n different partial assignments to try, 3 to the n different ways, no more than that, right? And so trying all the ways, I want to check whether it's the constant function, right? I want to check whether it's the same. So is it most 2 to the n bits to check, actually fewer usually, to check if the function is constant, right? So after choosing a partial assignment, that's restricting the truth table, right, to some subsequence of the truth table. I just want to check whether it's all ones or all zeros. Okay, so this is polynomial in 2 to the n. Okay, all right, and it's also large. Okay, so this is something that's going to be true of a random function. A random function is not going to be constant with high probability over all the different ways to set partial assignments. Okay, right. So suppose like the property is false. Okay, so there's some way in which we can assign the function like a partially and get a constant function, right? That's just saying just negating a condition up here. There's some partial assignment we can set. We make the thing a constant function. And the claim is that for any such function with this property, we can encode it in strictly less than 2 to the n bits. There's a way to uniquely encode such a function in less than 2 to the n bits. And so that means that the total number of such functions must be much less than 2 to the 2 to the n, right? So if the claim is true, then there's at most 2 to this encoding length functions for which the property is false. Okay, and so then the probability the property is false is actually just going to be little o of 1, right? So this is the total upper bound the number for which it could be false is the total number of functions, and this is the denominator is much bigger than the numerator. Okay, for a sufficiently large n. Okay, so this is the claim. So in other words, if there is some partial assignment on which the function becomes constant, then we can get this really efficient encoding. So it can't happen for a random function with high probability. So here's a proof of the claim. And this is where we use the, the constant 2. I had like a 2 in there for a mysterious reason. And that's exactly the same 2 as this 2. Okay, the n squared. So right, I'm subtracting n squared and I'm adding 2n minus 1. That's right. So this is significantly less than 2 to the n. That's important. All right. So, okay. So how do we prove that we can do this re-encoding whenever it becomes constant? The idea is that if I tell you, let's say I tell you the partial assignment, okay, to assign to these variables. So that takes at most like 2n bits. I mean, like technically, right? I just have to tell you like whether something is not assigned, or whether it's 0, or whether it's 1. Okay, so there's a very crude upper bound. It's like just 2n bits. Okay, so then I use like 1 bit to specify what constant it actually evaluates to after that. Okay, so what I'm doing here is I've got the truth table to the n, right? I'm telling you some partial assignment, okay, to set, and I'm telling you on the remaining bits. Now the remaining bits is 2 log n. On the remaining bits, it's a constant, right? So I'm just telling you that constant. And the point is there's like n squared bits that are now determined, right? If I set up all but n minus 2 log n bits, variables, then the remaining truth table is 2 to the 2 log n size. And so there's n squared bits kind of left, but this 1 bit is describing its value. It's constant on that, right? So the point is I can use 2 to the n minus n squared bits to encode the rest of the function. So I've specified this partial assignment, which specifies like these n squared indices. I've told you it's constant on those. And so I just have to tell you the rest of the bits. The n squared 2 to the n minus n squared bits of the rest. Okay, so it's just like an encoding argument to show you that like setting a partial assignment that relieves 2 log n or order log n variables free, but makes the thing a constant is actually, this cannot happen for a random function. There's not that many functions for which this is true. Does it make sense? Are there any questions about this part? But, I mean, sort of a lot of arguments
Yes.
about like the naturalness of properties where this. Yeah.
Yeah, seems no questions at this point. I do not see at least. So
Okay.
maybe if anybody has any question.
Okay. Cool.
Doesn't seem so. No?
Yeah. So the point is, a random function is going to satisfy this kind of property. It will. Yeah, it makes sense that it's going to be non-constant, even if you set a whole bunch of things. It's just because it's random. If you leave like n squared bits there, it's probably not going to be constant. Okay, so the big theorem of Rasborov and Rudich says the following. Okay, so there are these various properties which are natural and more complicated ones I didn't describe. And they're used to prove these lower bounds against these weak classes like the AC0. Okay, they say suppose there is a natural property useful against P/poly. So this, the bigger class, the class of just polynomial size circuits with no extra restrictions. Okay, then there are no pseudorandom functions, which I will define later, in P/poly. Okay, and moreover, like this connection holds not just for P/poly, but for like things like constant depth circuits with majority gates in them. That's TC0. Log n depth circuits, things like this. If you manage to get a natural property against them, then there's no pseudorandom functions in this class. Okay, essentially no exponentially secure one-way functions. All right, so I will unpack a bit what this means. So it says, if we believe in cryptography, then no natural property can be used to prove lower bounds, actually even against TC0, for the following sort of reason. So Naor and Reingold showed that integer factoring is not in 2 to the, if it's not in 2 to the n of the epsilon time for some epsilon, then there are no natural properties useful even against TC0, which is constant depth majority gate circuits of polynomial size. So you allow majority as like one of your possible gates, where you allow unbounded number of inputs into majority and negations. So and this already holds, I guess, for TC0 depth 4. Okay, so and integer factoring can be replaced with other things, I think like discrete log and whatnot, like, you know, the things that we often base cryptography on. So the upshot is that, like, you cannot prove strong lower bounds via natural properties without breaking cryptography. Like, even lifting to like this constant depth majority gate from like constant depth or and XORs or something. So the idea is that lower bounds based on natural properties are self-defeating. They kind of do too much. Like, they have some algorithm in there that is used to prove the lower bound. But the problem is this algorithm is doing like so much it rules out average case lower bounds, which we think would be useful for cryptography. Yeah, so they rule out these stronger average case lower bounds, like showing that like these various functions are hard on average, like let's say on the vast majority of inputs, like you still can't approximately compute the function, right? So this is like the major lesson of this Rasburov-Rudich barrier, that natural properties, they arise naturally, I guess, like improving like circuit lower bounds, but there's as far as we understand about cryptography, there is a barrier to how far they could be used and how far they could go. If you believe in cryptography, then you should not believe natural properties, you know, will work. That like these common techniques which eventually identify some algorithm that can distinguish easy from hard in this way, they can't possibly work. All right. So let me talk about how does the proof go? Okay, but okay, before I give you the proof, I need to tell you what a pseudorandom function is. Okay, so for the purposes of this discussion, I will say it this way. So let epsilon be some parameter. An epsilon pseudorandom function. It's a polynomial time algorithm that takes 2 inputs of the same length, okay, R and X. You think of R as like a random seed, and then X is like the function you get after plugging in the random seed. Okay. Okay, so this F, the idea is it's a polynomial time algorithm, but you plug in a random seed, and it's supposed to behave like a random function over the input X. All right. It's supposed to look like a random function. And the usual way in which we try to define that it looks like a random function is to talk about distinguishability. Okay, so to say that like no interesting algorithm can distinguish this function F from a completely random function. Okay, so to formalize this, we say like for every randomized 2 to the order n of the epsilon time algorithm, D, that takes an oracle. Okay, so it takes in some oracle. It will either take in capital F, our polynomial time algorithm, or it will take in little f, a completely random function. Okay, and we're going to say F looks random to D, this star property holds. So the idea is, okay, D doesn't know whether I'm giving it capital F with a random R plugged in, or whether I'm giving a completely random F, like I'm talking 2 to the n random bits, right? Like in one hand, I have n random bits here. On the other hand, I have 2 to the n random bits, okay? So I want to know, okay, what's the probability this thing outputs 1 on one of the ends? So like the input's giving it nothing. It's just querying this oracle, and it's trying to determine, okay, am I given a polynomial time algorithm that's only got n random bits in it, or am I given a completely random function, right? And if we're going to say it looks random if the difference between these probabilities is negligible. It's less than 2 to the n of the epsilon. Okay, so the point is that, like, you know, you can imagine it could distinguish if one of these probabilities was high, one of these probabilities was low, and it just ran the thing enough times, you know, like 2 to the n of the epsilon times to check that they're different. And it takes 2 to the order n of the epsilon time, so it could do this, right? So this is like the usual indistinguishability notion that comes up in cryptography, pseudorandomness, and so on. So the upshot is that D can't distinguish between this function f, which is polytime and has only n random bits in it, and a random f, which is 2 to the n random bits. Okay, like for every single algorithm that's trying to distinguish between random function and this polytime capital F, it manages to fool it. Like it will, like whatever probability it has of outputting 1, it will be the same as if it had a random function within like some tiny negligible amount. All right. Okay. So, all right. So these are, okay, let me just say these are widely believed to exist, right? These things are widely believed to exist, and you can construct them based on the hardness of like factoring, discrete log, like other problems. So, all right, so we want to prove that if we got a natural property, A, that's useful against, let's say, size to the end of the 2C circuits, okay, then we can define a distinguisher that will actually break every possible candidate for a PRF. So we can come up with one distinguisher that breaks every possible F. Okay, it will all, in other words, this inequality will always be violated. It will all, like this difference will always be at least 1 and 2 to the n of epsilon. Okay, all right. So the way this works is we use the natural property, and we use like the conditions of this natural property to construct such a distinguisher. So the way it works is as follows. So our distinguisher is based on this epsilon. Okay, we've fixed some epsilon. It's going to get a function f. Now, okay, either this function is capital F or it's a random f. Okay, yeah, I mean, technically I probably should have put something other than f little f here, because this is just supposed to be an oracle that it's querying. Okay, so the idea is on all inputs of length into the epsilon, it's going to query f on all strings that have n minus into the epsilon leading zeros. Okay, so it's just querying it on 2 to the n of the epsilon strings. All right. All right. Then it forms a truth table made out of those strings, right, in the natural way, right? It forms it's got 2 to the n of the epsilon bits. You can just write it as a truth table. Okay, this is a string of length 2 to the n of epsilon. Okay, then it just runs the natural property on this f prime and outputs its answer. Okay, now we're going to claim that given the conditions of natural properties, this D is actually a distinguisher. It breaks all pseudo random function candidates. So any polytime algorithm which is trying to fool you will not fool this distinguisher. And the key idea is that this natural property is doing something different on random functions than on easy ones, right? That was part of the condition, is that on random functions, it's declaring hard. On the easy functions, it's declaring easy. That's exactly what's being used here. So first, this D sub epsilon runs in polynomial in 2 to the n of epsilon time, right? So it meets the condition up here, okay? In fact, like it's a deterministic distinguisher. Now, suppose we have some candidate function for our pseudorandom function, okay? And it takes n-bit randomness. It, on this, it's a function on n bits. And this thing runs into the C time, okay? So by standard arguments, this thing has at most the 2C size circuits, like by just translating algorithms into circuits, okay? And that's true for every single R. So like this circuit will actually take in the R and take in the X and give you the answer, okay? So so this distinguisher, so if it's given this capital F, it will construct this f prime, but this f prime has also small circuits. The reason why is that this f prime, right, we're querying it, it's just the result of querying capital F on these inputs, right? So if we just hard code zeros into capital F, we'll get a circuit for f prime. So if capital F has small circuits, f prime has small circuits, all right? Now, the fact that the algorithm is useful against size n of the 2C means that this algorithm is going to output 0 on f prime, okay? And it's going to do this for every choice of the randomness R. For every choice of the randomness R, it still has small circuits. So that means the probability over every R that the distinguisher on capital F outputs 1 is just 0. Okay, it always, It always outputs 0, regardless of the randomness, right? So it outputs 0 when it sees something that's actually easy, when it sees like a pseudorandom function candidate. On the other hand, if it sees a random function, then that this is the same as like just giving f prime a random f prime to our natural property, but by largeness. By largeness, this thing is going to output 1 on a non-negligible fraction of inputs. And this, so by usefulness, it says 0 on all the easy things. By largeness, it says 1 on random things. So therefore, this inequality does not hold, right? This inequality was saying the difference between, let me highlight, difference between like this probability and this probability is supposed to be negligible. Sorry, this one, I guess. Okay, the difference between this probability and this probability is supposed to be negligible. Let me go, see? So this one and this one is supposed to be small. And what we're showing is that actually using a natural property, it can be non-negligible. All right, so what we get as the upshot is that for every epsilon and for every constant c, for every n to the c time f, there is some sub-exponential time distinguisher so that the inequality does not hold. So there's just no pseudorandom function of this kind. Okay. Looks like I'm running short on time. I mean, this will just take a few more minutes. Are there any questions?
We have 10 more minutes for this part, right?
Oh,
yeah, okay, because we started 10 past, right?
I got confused.
Yeah, so. Sure.
Okay,
yeah.
Great. All right, so now let me definitely pause in case there are questions about this argument. But I mean, if you think it's easy, then you probably didn't miss anything. Isn't the input size of f prime different from f, so its circuits are relatively bigger? Yeah, that is true. Yeah, that is true. That I mean, in terms of its input size, yeah, I mean those circuits are bigger. So yes, I guess technically you want to be careful about like about the input length here. That like it will be polynomial. Like you need usefulness against something slightly polynomial. Yeah, thanks for pointing this out, because like its input length is into the epsilon, and if the so in terms of its input length, so maybe write it like this. Like in terms of its input length, call it m. It's like m to the 2c over epsilon size, where its input is of length into the epsilon. Yeah, so you do need usefulness against like something slightly polynomially larger. Yeah, thanks for.
Thank you.
Yeah, you are paying attention. Thanks. Good. Yeah, but really, like it's just like these properties of these properties of natural property just kind of automatically make this follow that they're killing all pseudorandom function candidates. Yeah, so okay, so the next question is, oh, how do you get around natural properties, right? It only has like 3 conditions on it, and they seem pretty useful, you know, by themselves or natural. Okay, so usefulness, I argued already, is necessary. Like if you're going to prove a lower bound, you've got to say like you got to have some property that says like these algorithms or these circuits are easy, whereas this function is hard. Something's got to say to tell the difference. Okay, so you want either to get around largeness, so like being true of random functions, or being constructive, meaning that you don't necessarily have an algorithm for determining the property. So which is the pathway, right? Going along with the title of the talk. So we got to avoid one of these. And I'm going to just say a parable or stories that I have heard from sources I will just leave unnamed about why you should avoid largeness and why you should avoid constructivity, because they kind of contradict each other. So why should you avoid largeness? The idea there is that specific functions, so if I'm proving lower bounds against a specific function, it's hard for a specific reason. You think of like a complete problem, right? Like for NP, it's got to have like really interesting structure it's not going to look random in a particularly well-defined sense. So it's going to be hard for a specific reason. And so we got to find properties that are true of specific functions, but are maybe just false of random hard functions. Okay. Yeah, maybe we have some property that just declares like literally everything easy except for except for this one function that declares hard. Okay, maybe your proof has to work like that. Another story you might tell yourself is, okay, you should avoid constructivity. And the idea there as well, I mean, it's an efficient algorithm for detecting hardness. I mean, one intuition is that P is in from NP is hard to prove because most reasoning is itself efficient. And you can actually see some formalizations of that if you look at efficient like proof systems like bound arithmetic or something. And so, the idea there, the story there is that we must go beyond such primitive reasoning. We must have like some properties that distinguish easy from hard, but are like, very complicated, not polynomial time computable, and so on. I mean, they both make sense, actually, on some level, but as I'm hiding with like some arrows, the moral is to avoid being large. And this is, I'd say, good health advice in general too. Yeah, you should avoid being large with your properties and yourselves, I guess. Hard to do in a pandemic sometimes. But the big theorem here is kind of unexpected, is that, okay, let's say we want to prove like circuit lower bounds at all. So if we're trying to prove p-poly lower bounds, we got to at least prove that non-deterministic exponential time is not in p-poly. Still a major open problem though. It turns out this condition is equivalent to there exists a constructive and useful property against p-poly. Okay, so we satisfy we have some properties satisfying 2 of the 3 axioms of a natural property. Okay, and this equivalence holds for many restricted class, almost any restricted class you could think of, like the TC0, the NC1s, and whatever, like all these restricted things, and even this ACC0 thing. So what this is saying is, like, if we believe in decent circuit lower bounds at all, like this one being like maybe not even decent, just embarrassing. If we believe in this thing at all, then we must believe in properties that are both useful, but actually run in polynomial time. They run in polynomial time and they distinguish some function from the easy ones. And let's say that like it just says, it just says everything is easy except for like, this one true special function. Okay. All right. So yeah, these are just restatements of each other in a particular formal sense. That I'm not sure how to even give like rough intuition for this, but I guess the idea is something like this condition is equivalent to some conditions saying that NX has like poly-sized circuits encoding its witnesses. And this was proved by IKW by Impagliazzo, Kabinetz, and Vigdorson. Okay, so what this means is that like for every NX verifier that you come up with, this is actually equivalent to NX in p-poly. Okay, right. So if NX is in p-poly, then other things are in p-poly, namely the witnesses for verifiers. So like if any verifier you come up with, there's like a small circuit in whose truth table encodes a witness. Okay, so the idea here is if I have a verifier, so if I have a verifier when NX is not in p-poly, I have some verifier such that all of its witnesses do not have polynomial size circuits. This verifier runs in time polynomial in its witness length because its witnesses are exponential, but it's also useful in the sense that none of its witnesses have polynomial size circuits. I don't know how to summarize this in an easy way, and I didn't really prepare to. But you know, if you have questions, we can try. But there's a sense in which like this very embarrassing open lower bound problem is just equivalent to having constructive useful properties. So there is some polynomial time algorithm which will distinguish some hard function from all the polynomial size circuit truth tables. Yeah, I guess I'm not prepared to like give much more explanation, and I've reached the hour, so maybe it's good to stop here for now.
Yeah. Any questions about it?
But yeah, please feel free to.
Yeah, or anything so far.
Yeah.
I have just a question, just that I check whether I understood correctly. So in this proof that you prepared,
yes,
that you have shown, you would break also all those PR those pseudo-random functions in like p/poly, right? Because you only needed that the existence of a circuit for particular ends. Yeah. Good.
Yes. Because the point is that our natural property will work against all polynomial size circuits, and so then our distinguisher will also work against all polynomial size circuits. Yeah.
Okay, I see that Mikael has another question. Is the exist on the right-hand side constructive to some extent? I'm not sure which right-hand side. Oh, yes, this one. Yeah.
This one here. Yes. Essentially, so in fact, I can tell you an explicit algorithm, I guess. You can write down an explicit algorithm, and NX is not in p-poly if and only if this one is useful. Sorry, I keep hitting my microphone. I'm sorry if it's like yeah. So like there's a explicit p-time algorithm. So the proof gives you an explicit p-time algorithm, and like A, and then the only that you need to show it's useful is you got to show NX not in p-poly if and only if A is useful. Yeah. So this thing is p-time. It's not trivial. It outputs 0 on, let's say, most strings it gets, but it outputs 1 on some strings, okay, infinitely often. But to prove it's useful is equivalent to proving NX not p-poly. So basically, this is the verifier. This is the verifier for some NX complete problem. So it's like I'm writing down, I've got some NX complete problem sitting over here. Okay, and I've got a verifier V for it. And there is some, I mean, I didn't tell you what the input is, but somehow the input can be encoded into the input link because the input is so small. So it's got some input encoded in it, and it's taking in some Y. And this Y is of link, let's say, to the N. And this thing runs, this verifier runs in poly to the N time. And right, so this thing is just checking whether a given witness makes the verifier accept or not. That's what the polynomial time algorithm does. It's just running the verifier on some implicitly encoded Y based on, let's say, the input link to the thing, and so implicitly encoded X and the input Y. And so this is just some verifier for an NX complete problem. Because it's not, I mean, because it's an NP complete problem, there are going to be like many X which it has a witnesses yes instance. So it's a non-trivial algorithm. Okay. For everything it's not a witness, it will output 0. If NX is not in p-poly, then it's actually useful, and it's useful. If it's useful, then NX is not in p-poly. So in other words, like if there are witnesses that don't have small circuits, then this is useful. But that condition is equivalent to NX not in p-poly, roughly speaking, by this thing up here.
And the next complete problem you have is also explicit, right? It's some sort of
you can
problem.
Yeah, you can. I suppose you could take any NX complete problem. I just took like a canonical one where you're verifying that a non-deterministic machine accepts within so many steps, or two to so many steps. But yeah, you can just write these things down, and the proof that they are useful is exactly requires index not in P poly, it's equivalent. Yeah. So it's funny. Like, so constructivity is just something inevitable for these things. If you're going to, like, you're going to have these properties. So might as well look for something constructive, I guess.
Thank you very much for that.
Sure.
Great. Any more comments, questions? Doesn't seem so. So I guess we can take some break now for 15 minutes to keep on schedule. So we can meet 20 past whatever hour is on your clock. Yeah, and continue to the third part. Yes.
Yeah. I'm going to use slides for this one. So
good. Yeah. We can already now put them on to see that this works.
Yeah, just go ahead and put it on to make sure it's going to work. Let's see. Oh, the part of this one. Can you see?
Yeah,
all right.
Works. Yeah.
Great.
Right. So yeah, in 15 minutes, 20 past, we continue with the third part. So yeah, take a time to stretch and not be large. Therefore,
right.
And we continue.
Avoid being large. Exactly.
Avoid being large. Yeah.
Let's see in a few then.
Yeah. See ya.